A pretty soul-crushing moment in my life was when I became obsessed with these breathtaking images of galaxies, nebulae, and deep space given to us by telescopes like Hubble and JWST. And then I learned that space doesn't actually look like that, at least not in the way that your eyes could ever see it. But the story of how we learn to see the universe like this is one of the greatest technological revolutions in human history. And I'm sure that it comes as no surprise, but space has fascinated me since I was a kid. I used to spend every summer on a small lake in Ontario, lying out on the dock at night, trying to find different constellations and hoping, if I was lucky enough, that I might just see a shooting star. And what I learned then is that there is a certain feeling you get while stargazing that you can't really get anywhere else. That childlike sense of awe and wonder, and the realization of just how small you are, while simultaneously being aware that you are a part of something so big that you almost can't even believe it. And that feeling, the mix of awe and smallness and wonder, isn't unique to me. Thousands of generations of humans that came before did the exact same thing and felt those exact same feelings. And it is genuinely amazing what we have been able to uncover through the advancement of space photography, the ultimate intersection between science and art, that is able to strike that same childlike wonder inside of us. And you can call me dramatic, but they do almost take your breath away. And it is really insane when you think about the fact that we are the first generation of humans in over 300,000 years to ever see our universe like this. The only problem is that isn't really what our universe looks like. But before we go there, we need to rewind a little, all the way back to the Lascaux Caves. Now, I personally love the story of the discovery of the Lascaux Caves because as a former teenage boy with a big imagination, this was always the kind of thing that I was hoping was gonna happen to me. It was Thursday, September 12th, 1940, and France had fallen to Nazi Germany just 3 months earlier. The world felt dark and uncertain, but on that calm afternoon in southwestern France, an 18-year-old boy named Marcel Ravidat was walking in the woods with his dog Robot. Marcel had grown up hearing local legends about a lost medieval manor that once stood on the hills of Montignac, and supposedly a secret tunnel had been built beneath it during the 100 Years' War, a hidden escape route, and maybe even the perfect hiding spot for treasure. And while this castle had been lost to time, locals believed that the tunnel and its treasure were still hidden underground. So, when Robot suddenly took off chasing a rabbit and disappeared into a hole in the ground, Marcel's imagination ignited. Inside the den, Robot's barking kept getting more distant, and Marcel realized this tunnel was a lot bigger than he originally thought it was. Could it possibly be the tunnel leading to buried treasure? The tunnel was too small for him to enter, so he pulled Robot out and returned a few days later with 3 friends and tools to dig it wider. And when Marcel finally slid down into the darkness, he wasn't surrounded by treasure, but something even stranger. Massive, prehistoric paintings all over the cave system. These masterpieces featured large animals like bulls, horses, and stags, created with mineral pigments in various shades, and are considered among the most significant prehistoric art that we have ever found. Paintings that we believe to be somewhere around 17,000 to 20,000 years old. And one specifically has been the subject of debate and theory more than any other: a cluster of small black dots hovering above it. Dots that some scholars believe might actually be stars. Specifically, the Pleiades cluster, which these Paleolithic hunter-gatherers would have seen vividly in their unpolluted night sky. And if that is what they were depicting, makes this painting to be the oldest depiction of space our species has ever created. In the millennia that followed, our depictions of the sky not only became more frequent, but more accurate as well. The Nebra sky disk, forged around 1600 BCE, depicts what is likely the sun, the moon, and the Pleiades. Babylonian tablets mapped constellations with startling precision, and ancient Egyptians charted the rising of the star Sirius to predict the flooding of the Nile River. But for thousands of years, we were still just drawing and mapping what our eyes could see. But all of that changed in 1609. After years of refining his own telescope, Galileo pointed it at the sky and peered deeper into the universe than any human being before him. He saw mountains and craters on the moon, proving it wasn't a perfect heavenly sphere. He discovered 4 moons orbiting around Jupiter, today known as the Galilean moons, and was the first direct observable evidence that not all celestial bodies revolved around the Earth. And then he watched Venus go through phases, proving it orbited the sun. For the first time in history, humanity wasn't just imagining the cosmos, we were actually observing it. And then, in the 1800s, we learned how to capture it. In 1840, John William Draper took the first photograph of the moon. 10 years later, William Cranch Bond photographed Vega, the first image of a star beyond our sun. And in 1880, Henry Draper and his wife Anna captured the Orion Nebula. And you know what? The fact that we were able to take a picture of a nebula from down here on Earth in the 1800s is still pretty insane to me, given the technology of the time. And it was around this time that we were learning something else, thanks to a German glassmaker named Joseph von Fraunhofer, who passed sunlight through a prism and noticed dark lines slicing through its rainbow spectrum. And he soon realized that these imperfections weren't actually imperfections at all, they were fingerprints. And each element on the periodic table would leave behind a unique pattern of lines in light when dispersed through a prism, which sounds way more complicated than it actually is, because all you need to know is that he learned that by studying starlight, we could actually determine what the stars were made out of: hydrogen, helium, iron. This was the birth of a field of science known as spectroscopy, and with the subsequent development of spectroscopes to view and spectrographs to record, astronomers were finally able to examine the makeup of stars. But there was one limit that we had yet to overcome. Every single picture that we could take of space was taken from the ground, heavily distorted by our planet's atmosphere. And eventually, we started asking a different question. What if instead of just pointing our cameras at the sky, what if we brought our cameras into it? Now, I hate to bring this up 2 videos in a row, or do I? But we have known the Earth was round for thousands of years, all the way back to the ancient Greeks. But what changed in the 20th century wasn't our knowledge, it was proof. And with the invention of aviation, we could finally climb high enough to see the Earth's curvature with our own eyes. In 1930, a photograph taken about 21,000 feet above Argentina captured something remarkable. The Andes Mountains, 287 miles away, appeared lower on the horizon than geometry would allow on a flat Earth. Mountains that were taller than the plane's altitude, sinking below the curve. Then, in 1935, Orville Anderson and Albert Stevens rose over 72,000 feet aboard the helium balloon Explorer 2, and from that altitude, higher than any human being had ever been before, the sky began to darken, the horizon started to bend, and the Earth began to look less like a landscape and more like a planet. But the real jump came in 1946 when a V2 rocket carried a camera 65 miles above the surface, just beyond the recognized edge of space. For the first time in history, we saw the Earth from outside the Earth. By 1966, satellites were sending back full disk images of our world, showing it as it truly is, a tiny floating ball drifting in the endlessness of space. Then came Apollo. In 1968, as Apollo 8 orbited the moon, astronaut William Anders captured a photograph now known as Earthrise, a picture released by NASA in an attempt to assert space exploration dominance, had a profound and unexpected impact on environmental awareness, transcended geopolitical ambitions, became a catalyst for the modern environmental movement, and sparked a global awakening to the importance of caring for our planet. But we still didn't stop climbing. On September 18th, 1977, Voyager 1 turned its camera back towards home from 7.25 million miles away, and for the first time ever, we saw the Earth and the Moon not as separate objects, but as one complete system drifting together in space. And then, on February 14th, 1990, from 3.7 billion miles away, Voyager 1 took one last photograph before turning its cameras off forever. The pale blue dot. Some people still don't understand just how significant this picture is, the absolutely insane technological achievements that even allowed it to be possible, but also just how powerful it is. Seeing the Earth, the only home that our species has ever known, taking up less than 1 pixel on the screen. And I could never do it justice, so I am gonna let one of the greatest of all time, Carl Sagan, do it for me.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization. Every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena.
And lastly, we have one of my favorite pictures of our planet called The Day the Earth Smiled. And I know you'll probably look at that picture and say, Thomas, man, that is a photo of Saturn. And you would be correct. That is a picture of Saturn taken on July 19th, 2013, from the sadly doomed Cassini spacecraft. But if you look closely, you will see the Earth right here. And what I love about this one is that the people of Earth received a notification in advance that Cassini would be taking this picture, and were encouraged to smile and wave at the camera. So all over the world, humans came together in huge numbers to have fun, smile, and wave at a camera that was 750,000 miles away. Some good old-fashioned human love and unity, and we could always use more of that. But there is a massive gap between pictures like this and pictures like this. And if space doesn't actually look like that, then are we just photoshopping these pictures for fun? The answer to that question is no, and the problem isn't actually the pictures, the problem is us. Because our eyes can only detect a tiny sliver of the electromagnetic spectrum, a narrow band that we call visible light. But our universe doesn't operate in visible light. It shines in ultraviolet, in infrared, in X-rays, and gamma rays. And from our position on the ground, Earth's atmosphere blocks the vast majority of it. It absorbs UV, completely stops X-rays and gamma rays, water vapor swallows huge portions of infrared, and even blurs visible light into twinkling distortions. Our atmosphere does a wonderful job at protecting us, but it also blinds us. So in the late 1960s, NASA asked themselves, what if we stopped looking at the universe through the lens of our atmosphere and actually went above it? That is where the OAO program began, the Orbiting Astronomical Observatories, humanity's first true space-based telescopes. And once we got up there, we saw the universe in a completely new light. Yes, that pun was intended. The core goals of the OAO program sounded simple on paper: prove that a telescope could survive in orbit, that it could point precisely, that its instruments wouldn't fail, that its data could make it home. In 1966, OAO-1 launched and failed within minutes due to a catastrophic power failure, and our first attempt at putting eyes in space had gone blind almost immediately. But you know what they say? If you don't succeed, try and try again. And 2 years later, we had our first success with OAO-2, more commonly referred to as Stargazer. Stargazer focused on something that we had never been able to properly study from Earth: ultraviolet light. Now, ultraviolet light sits just beyond the violet edge of the visible light spectrum. You can't see it, but you can definitely feel it. It is the exact same thing that will burn your skin on a bright summer day when the UV index is high. And in space, UV light reveals something extraordinary. If you follow UV light to where it's the strongest, you find the hottest, youngest, and most energetic regions in the entire universe. Massive newborn stars, violent stellar winds, and glowing clouds of ionized gas, all invisible to the naked eye. And then came OAO-3, also known as Copernicus. Launched in 1972, Copernicus studied ultraviolet light with unprecedented precision, and it confirmed something profound. The space between stars isn't actually empty. It was filled with hydrogen gas, the raw material for future stars. We were learning secrets of how the universe was born in the darkest reaches of time and space. The OAO program was a complete success. It proved space telescopes were viable. It demonstrated precise pointing and stability, produced major scientific discoveries, and built technical confidence inside of NASA. And it was that success that paved the way for something even more ambitious: the era of the Great Observatories. And for the first time in history, we weren't just building a telescope, we were building an entire fleet. And not to see the universe in a better color, but to see it in every form of light that it emits. It was like for all of this time, for all of human history really, we were only seeing the universe with one of our senses, and all of a sudden, we were able to perceive it in all of them. The Hubble Space Telescope launched in 1990 and gave us some of the most iconic space pictures of all time. It gave us the deep field images, revealing thousands of galaxies in what looked like empty darkness. It showed us the pillars of creation, towering columns of star-forming gas, and it helped us refine the age of the universe to 13.8 billion years. And through observations of distant supernovae, it contributed to one of the most shocking discoveries in modern science. The expansion of the universe isn't slowing down, it's actually accelerating. And something, which we now know to be dark energy, is pushing space apart. But visible light was only the beginning. In 1991, the Compton Gamma Ray Observatory began studying the universe's most violent events: gamma ray bursts, explosions so powerful they can briefly outshine entire galaxies, colliding neutron stars, matter annihilating itself, the most energetic phenomena since the Big Bang. The third member of the Big Four was the Chandra X-ray Observatory, designed to observe high-energy X-rays from extremely hot cosmic sources. Black holes shredding stars, supernova remnants expanding into space, galaxy clusters filled with gas, heated to tens of millions of degrees. By mapping hot gas in galaxy clusters, Chandra showed us that most of the universe's mass isn't visible. It's gravitational, invisible, and dominant. Something we can't actually see at all. Dark matter. The fourth and final mission of the Great Observatories program was a NASA infrared observatory launched in 2003 called the Spitzer Space Telescope. Designed to study the universe in infrared light, it transformed understanding of cool cosmic phenomena from forming stars to distant exoplanets, nebula hidden inside dark clouds, and even the structure of our galaxy. Each telescope is designed to look at a different wavelength of light, and each one reveals a different layer of reality. Visible light, gamma rays, X-rays, and infrared. These didn't just give us better pictures, they gave us a multi-layered universe, far beyond what the human eye could ever see. Which is why you'll hear people say, the universe doesn't actually look like that, including me in one of my most viral videos. And technically, they are right. If you were floating in space next to a nebula, your eyes wouldn't see glowing purples and electric blues. They'd see almost nothing, because many of the wavelengths that these telescopes detect are completely invisible to us. And what we're actually looking at in these pictures is data. The filter of one telescope could show us visible light, another shows us ultraviolet light, and a third shows infrared light. Astronomers will then assign colors that we can see to these invisible wavelengths, not to deceive us, but to translate. This is a process called false coloring, and it allows scientists to reveal structures, temperatures, and chemical compositions that would otherwise remain hidden. The colors, the textures, the glowing clouds, they are just translations. Physics being turned into imagery. You aren't just looking at the universe, you're seeing it in every form of light that it emits. Which is why I have to call back to when I said this is the ultimate intersection between science and art, or using art to better understand science. One of the last pieces of this puzzle, for now at least, is that when we look out into deep space, we aren't just looking across distance, we're actually looking back in time. And because those galaxies that formed in the earliest days of the universe are so far from us, their light has been stretched so much that it has gone through something called redshifting, putting it at the far end of the red side of the electromagnetic spectrum. And to see that nearly invisible light, we needed something colder, larger, and more sensitive than we had ever built. A 6.5 meter mirror coated in gold, a sunshield the size of a tennis court, operating at nearly -223 degrees Celsius. Parked 1.5 million kilometers away from Earth, the James Webb Telescope is not just the next Hubble, it is an infrared time machine, allowing us to look deeper into the universe's history than ever before. And it is so sophisticated that it can also analyze the atmospheres of exoplanets, identifying water vapor, carbon dioxide, even methane, molecule by molecule. And already, we have identified possible biosignatures, which is the chemical or physical indication of the presence of life on another planet. JWST is the culmination of thousands of years of everything that came before it, from cave paintings to sketches to blurry pictures of our own planet, to seeing the universe across its entire electromagnetic spectrum. And it is just the beginning of something so much bigger. The VRC Rubin Observatory will map billions of galaxies and track the changing sky in real time. The Nancy Grace Roman Space Telescope will hunt for dark energy and thousands more exoplanets. Future missions may directly image Earth-like planets, searching for biosignatures, and maybe one day a spectrum will come back with oxygen, methane, and water in the same atmosphere, and our understanding of what is really out there in the universe will be completely upended once again.